Hello everyone, this is the highlight video for this week. This week's unit is on energy, which is a little abstract, so I wanted to start off with some definitions here. So when you think about energy, I want you to think about motion. So all energy is related to motion. We have two types, the kinetic energy, which is the energy associated with the movement of an object, and the potential energy. This is the potential to cause things to move, okay? So again, all energy, there's two types. There's kinetic energy, which is with movement, and potential energy. So inside potential energy, there's gravitational potential energy, electric potential energy, chemical potential energy, spring potential energy, as well as thermal energy, okay? So lots of different subtypes here, but the main ones are kinetic energy and potential energy. So equation-wise, for kinetic energy, we have this equation here, 1/2 mv squared. M is the mass of the object, and v is the speed of the object. Now, when you plug in the metric units here for kilograms for mass and meters per second for velocity, the unit we're going to get out is joules. So always when you're plugging in, be sure to plug in the metric units here. So if I give you some numbers, like the mass of the ball is 0.145 kilograms, the velocity is 40 meters per second, we can just plug that into our kinetic energy equation and get a number out here. In this case, 116 joules of energy. Now, we have all these forms of energy here, okay? So energy is going to transfer from one form to another, and the scientific word for that is work. And so we have an equation for that as well. Work is the force applied to an object times the displacement of that object. Now, there's this parallel symbol here, so only part of the force that's in the same direction as displacement or the opposite direction of displacement will apply work, will transfer energy from one form to another. So let's do an example here. Let's say I have this man who's trying to stop this rolling car. So it's rolling down, he's applying a force, trying to bring it to rest. So while it's moving, he's applying a force of 600 newtons, and the car travels a displacement of 15 meters, okay? So let's look at what force and displacement directions are going to be. So do you see how the force is to the right? So he's applying a force to the right while the car moves to the left. So the car starts off with a lot of kinetic energy and ends up with no kinetic energy. So he is removing kinetic energy from the car. And because he's removing kinetic energy from the car, he is doing negative work on the car. We can also know that's true is because the force is the opposite direction of displacement. So because these are opposite directions, the work is going to be negative. So when we start off with our equation, the force here is 600 newtons and the displacement is 15. But because these are opposite directions, we get a negative sign here. So please don't forget this. You always got to look and see, is my work going to be positive or negative, and think about what direction the force and displacement is going to be. Then we can plug in our numbers here, 600 newtons for force and 15 meters, and we arrive at work of negative 9,000 joules. So he removed 9,000 joules worth of kinetic energy from the car by pushing it to a stop here. Similarly, let's say he is now trying to get the car started from rest. So we want to figure out how much work he's doing here. So the car starts at rest, he applies this force, it moves at some distance d. How much work is done in the car? Well, what do you think? Is this going to be a positive amount of work or a negative amount of work? So he's adding energy to the car, right? The car's gaining kinetic energy. The displacement's to the right and the force is to the right. So that means that this is going to be a positive amount of work. So when we plug this in, we don't have to worry about that negative sign because the work is positive. So the force is 300, the distance is 10 meters. Multiply those together, we get 3,000 joules of energy. So he's added 3,000 joules of kinetic energy to the car. What about pushing a stationary wall? So let's say he pushes with 3,000 newtons. This is a lot more force than what he was doing before. How much work has he done on the wall? Well, if your answer is 0, you're correct. So work is force times displacement. Well, if the wall hasn't moved at all, doesn't matter how big your force is, if the wall hasn't moved, we still get 0 joules of work. And this makes sense if you think about it. The wall hasn't gained or lost any kinetic energy. So because this kinetic energy hasn't changed, we're not doing any work on it. No matter how hard we push, we're not giving it kinetic energy, so we're not doing any work on it. Power. So power is another way that we're going to be using work, and that is just the rate at which energy is transferred from one form to another. So we're just going to do average power in this class, and that's just the work that you do divided by the time it takes you to do it. So the units of power is work. So anytime we use is watts, watts. Anytime that we solve for work, we want to keep it in metric. So this will be joules. Same for time, needs to be in seconds. And if we do that, we get watts, which is a capital W for watts. I like to use lowercase w for work, so it's kind of more clear what you're doing. So joules per second for power is watts. Back to this example here, same thing we did before, but I added one more question here. If it takes him 30 seconds to move the car 10 meters, what was his average power? So all we have to do is we've solved for work already. We can just divide that by the time, 30 seconds. 3,000 divided by 30 gives us 100 watts of power. So this is a concept I've been saying a lot, but we actually have an equation for it. So the work done in an object equals to the change in kinetic energy of that object. And this is what's called the work energy theorem. This delta symbol here, this just means change, which is the final minus initial. So I'm going to plug that in. So the kinetic energy final minus the kinetic energy initial. Now we have an equation for the kinetic energy, so we can plug that in as well. So the total work is equal to 1/2 mv final squared minus 1/2 mv initial squared. And so let's go ahead and put this to use. Let's say I have this car that's driving and it slams on its brakes and comes to a rest before it reaches this intersection. So the force that the brakes apply is 50,000 newtons, and the mass of the car is 1,500 kilograms, and it travels 24 meters. The question asked is how fast was it traveling right before it hit the brakes? So we can use the work energy theorem here. The total work done is equal to the change in kinetic energy. So there's two parts here. We got to calculate what the total work is, and then we can plug it in here to get this. So when we're calculating work, we need to remember, is the work positive or negative? So what do you think? The car's traveling to the right. The force of the brakes is to the left. So is this going to be a positive work or negative work? If you say negative, you are correct. The car's moving to the right. The force is to the left. These are opposite directions. So this is going to be a negative amount of work. So when we plug in our work equation, we get the negative 50,000 newtons that we're told, right? The brake's 50,000 newtons, multiplied by d, the displacement, 24 meters, and we arrive at negative 1.2 million joules. So 10 to the 6 is million. Well, that's the first half. We can take that number, plug it into our total work, equals the final kinetic energy minus the initial kinetic energy. Well, we know the mass of the car, that's 1,500. The final velocity is 0, so this whole term is kind of gone because anything multiplied by 0 is 0. And the initial velocity, that's what we're trying to figure out. So we got a bunch of numbers here. Let's kind of simplify this down. We get 1,600 equals initial velocity squared, take the square root of both sides, and we arrive at initial velocity of 40 meters per second. So I mentioned these energies before, but we have two more I want to talk about, and that is gravitational potential energy. So this is potential energy of gravity, this subscript here stands for gravity, equals mgh, the mass of the object, times g, which is 9.8 on Earth, h, which is the height above a reference point. So we're always going to choose the ground to be a height equals 0. That's going to be our reference point. So here I have this boulder. Let's say it's 5 kilograms. It's a height of 27 meters above the ground. How much gravitational potential energy it has. We can just plug those numbers into our equation. So m is 5, g is 9.8, and h is 27. Multiply those together, we get 1.3 times 10 to the 4th joules. Now let's talk about springs. This is the potential energy of a spring. The equation for this is 1/2 kx squared. K is the spring constant. This is how stiff the spring is. So a larger spring constant would be, it'd be harder to stretch and harder to compress than a smaller number spring constant. Now x here, this is the distance from equilibrium. So when a spring is just resting at equilibrium, if you stretch it, 0.1 meters, then x will be 0.1. Okay, and it is squared, so compressing that negative 0.1 becomes positive 0.1 squared, so it goes away. So let's calculate this. Let's say I take this spring and I pull down on it and I stretch it 0.12 meters from its unstretched length, from its equilibrium length. And I tell you that the spring constant is 15 newtons per meter. I can just plug that into our spring equation. 1/2 kx squared, k is 15, x is 0.12, and I can multiply that out to get a potential energy of 0.108 joules. This brings us to conservation of energy. So the total energy at any point in time equals the total energy at any other point in time. So we're not gaining or losing energy along the way. So we have our three forms of kinetic energy so far. Three forms of energy: kinetic energy, gravitational potential energy, and spring potential energy. So initially we can have three forms: kinetic energy, spring potential, and gravity potential. And at another point in time, we have three forms of energy: kinetic energy final, spring potential final, and gravity potential final. And we can plug in our equations for all of these. So kinetic energy 1/2 mv squared, potential energy 1/2 kx squared, and so on for each of these terms. Now there's a lot going on here, okay? But each of these problems, a lot of these are going to be zero, and I'll show you what I mean here in this next example. So here I have this marble that I'm going to compress on a spring. So I'm going to compress the marble, this 0.05 meters, and then I'm going to release it from rest. The marble is going to be pushed by the spring. It's going to roll up to some point here before it rolls back down. My question is, how high does it roll up to? We can solve this with conservation of energy. So these are all those forms of energy, but we released it from rest. So do you see how our initial energy, our initial velocity is zero? So our initial kinetic energy is zero. The spring is compressed initially, so we do have energy here. Now the marble's on the ground here, so our height initial is zero, so this term was all gone. At the highest point over here, the final velocity is zero, and so the final kinetic energy is zero, as well as the spring is going to go to rest. That is going to go to its equilibrium position here, isn't it? So after the marble leaves, the spring is going to go to its equilibrium position, so x final is going to be zero. So 4 of these terms are gone, and all we're left with is our initial spring potential energy equals our final gravitational potential energy. And we can just plug our numbers in here. We're told k is 250. We're told x initial is 0.05. We're told the mass is 0.02 kilograms, and g is always 9.8. And then we want to solve for the final height. We have all of our numbers here. We can solve for final height. Gives us 1.59 meters. Last example. Here we have a boy. He's throwing this stone up and into the water. So he throws it at 5 meters per second. The stone has a mass of 0.2 kilograms. The initial height above the water is 7 meters. And we want to figure out how fast is it traveling right before it hits the water. So again, we have all of our big equation here, but a lot of these are zero. It is traveling at some initial velocity, so this term is still not zero. There is no spring, so this whole spring term's gone, as well as this whole spring term. Our initial height is 7, so this term is not zero. This is right before it hits the water. We want to solve for that velocity, final velocity. So this final velocity isn't zero. It's always right before it hits something, okay? Again, like I said before, the spring potential is zero because there is no springs. And the final height, this is the stone is at the water at the final point, so this is zero. So all of these terms are zero. And so we're left with just 1/2 mv squared plus mgh equals 1/2 mv squared. This is the final velocity. Well, we have all of our numbers here. Let's go ahead and plug it in. The mass is 0.2. The initial velocity is 5. The mass is 0.2. G is that 9.8. The initial height is 7, right? 7 above the ground, or above the water in this case. And our mass is 0.2, and the final velocity is what we'd like to know. So we just have our equation with numbers. We simplify it down, and we arrive at 12.7 meters per second for our final velocity. All right, that was a lot of equations. I put them all together here in this slide, so please use this as a reference as you're working on the assignments for this unit. These are all really related to each other, so sometimes it can be challenging to figure out which one needs to be used. Well, just start one direction and see which one you have enough variables to be able to use, okay? All right, I hope this helps.